chapter 6. Then I will call this maybe chapter 6b, strings and springs. Now, this is like something that is going to affect the physics and how we're going to solve problems. Then, when you pull on a string or a rope, it becomes taut, and we say that there is a tension in that string. The thing that I want you to know that in the same string, we have the same tension. Okay? Now, I will say, ideally, this is not the situation, because if you have something suspended from a string, that string, of course, or that cable, it should have weight. And of course, because of that, you will find that the tension at tension 1 is different from 2, from 3. Here we will assume always that all ropes, strings, wires, etc. are massless unless otherwise stated. Now, strings and springs, we will always also assume that there is, for now, an ideal pulley. That one is just now simply changes the direction of the tension, and it does not have a mass, it does not have frictional forces, and this is the reason that we are going to say here that the T equals the T, like the two tensions are the same. I want to show you like a video here. All right, and this is from your textbook. It's taking time to reload. Okay, maybe I want to check my internet. Okay, let's have that one. Is gonna maybe easier to reload. All right, and let's go back here. Yes, now it is loading. And okay, the one that I want you to watch is this one.
In this demonstration, I have 3 wood blocks. They are all identical wood blocks. They all weigh the same. If you take a look at the weight of the blue block, you can see it weighs about 18 newtons. Now with this setup, I have a spring scale between the red and yellow blocks. And the question is, what does the spring scale read? Does it read 0 newtons, 18 newtons, or 36 newtons? So the scale reads about 18 newtons. Now why does it read this and not 0 or 36 newtons? Well, the system is not accelerating, therefore the tension in the string between the yellow block and the spring scale must be equal to the weight of the block, which is 18 newtons. Another way to look at this is if you were to remove the red block and either hold the scale with your hand or attach this rope to a wall, the scale would still read 18 newtons.
All right, then now we are going to go back to the lecture. And here we're going to try now solving problems that they have strings or cables or, any like type of tensions that we are going to work on. And here we have a 50-kilogram person takes a nap in the backyard hammock. Both ropes supporting the hammock are at an angle 15 above the horizontal. Find the tension on the ropes. And of course here we will, of course, because the angle is the same, we know that this is going to be symmetrical. And then both they're going to be TT and there is MG. There is no normal force here. The reason that this object is not resting on a surface. I can apply sigma fx equal 0 because it is equilibrium. It's not having any acceleration, it is at rest. Then t cosine theta minus t cosine theta equals 0. And if from that, I will say for the vertical, sigma fy 2t sine theta minus mg should equal 0. I can use this one to calculate t, which is going to be 946 in newtons. Now, with springs, we know that we are going to deal with so many situations. We have springs, and I will say there is a spring that we are going to call it ideal spring. This one is characterized by a spring constant K, which is the measure of its stiffness, and it is measured in newtons per meter. Now, if we will try to pull the that spring with a force, then the spring itself is going to respond with a force that is going to be in the opposite direction of the motion. This is the reason why we have this minus here. This minus is not for K. This is for the displacement, and the displacement, it's in the opposite direction of the force. This is known as Hooke's law, okay? And actually, we use it widely. We have the same situation where we are going to compress the spring, and here we will say that again that the force from the spring is going to be opposite to the displacement, and it will obey the same law. Okay, I want to show you also another demo here from the textbook, and that one is the following. Okay. This is like very interesting.
Jeopardy is one of my favorite shows on TV. One night I'm watching it, and one of the categories was physics. That was fun. I was doing pretty well on that category. But what was really neat was when they showed one of the clues. It was a video clue, and Jimmy from the Clue Crew did it with a slinky. And the thing that was really neat about it was he did a demonstration I'd never seen before. And I thought it was pretty cool, so I'm going to do it for you right now. What I'm going to do is suspend a slinky, just let it hang by its own weight. I'm holding on to the top end, it's at rest. What I'm going to do in a moment is let go of the top end. And the question is, what will happen to the bottom end of the slinky? Will it drop immediately? Will it stay at rest for a few moments? Or will it move upward? Well, let's give it a try, see what happens. We'll do it first in regular speed, and then we'll see it again in slow motion. But I think even in regular speed, you can see what happens. Okay, so here we go. Watch the bottom of the slinky. Did you see that? The bottom end of the slinky stayed put for a few moments as the top end fell down to it. So the answer is 2. The bottom end remains at rest for a few moments. So why does the bottom stay at rest for a while? Well, as it's hanging there, you can see that the coils are stretched. These stretched coils exert an upward force, and it exactly balances the downward force of gravity. When I release the top end, these coils are still stretched, so they're still exerting an upward force. The bottom end will still stay there until the top end gets to the bottom and collapses all of these coils. Then it all will fall together. I think we can see it even more clearly if we try a longer slinky. Let's do that. Now here is a good size slinky. One more aspect of the slinky experiment is to compare the fall of a slinky with the fall of a ball. Of course, this ball simply drops with the acceleration due to gravity. But what about the slinky? We already know that the bottom of the slinky stays put initially. It doesn't fall at all until the top gets down to it. But what about the top of the slinky? If I release the slinky and the ball at the same time, how will their falls compare? Well, let's see. Let's see which one falls with the greater acceleration. Clearly, the top of the slinky went down with an acceleration greater than free fall. Why is that? Well, it's basically the same reason that the bottom stayed put. The bottom stayed put because the stretched coils above it pulled up and countered the force of gravity that was pulling down. The top of the slinky, the stretched coil, is pulling down on the top of the slinky and makes it accelerate downward with an acceleration greater than the acceleration of gravity, which is what the ball in free fall is doing. Now, of course, for the slinky as a whole, if you look at the center of mass of the slinky, that falls with the acceleration of gravity, just like the ball does. Isn't it amazing the kind of things you can learn about when you're watching TV? Who knows what you're going to find?
Okay, then this is talking about like springs, and here we have a problem where I have a 52 Newton backpack begins to slide when the spring K is 150 Newton stretches by 2.5 centimeters. What is the coefficient of static friction between the backpack and the table? Okay, now of course here we need to also analyze the forces on the that I would say backpack, and we will find that there is a force of static friction it is Fs equals mu s times n, and it is because it's gonna we want to have it when it begins to slide, and this is the reason why I will use the maximum value of friction. Let's write this maximum here. And that, of course, is gonna be equal to the force by the spring, and then mu smg equals kx. Then I will be able to find the mu s as kx divided by mg. Okay, there is a term that we are using usually when the objects are not really in translational acceleration. They don't have that linear acceleration. We call this translational equilibrium according to Newton's first law, sigma F equals 0. And this allows always to calculate a few forces that they are really unknown. And when we can have this situation, as I said, the object is going to be moving with constant velocity. For example, here we have forces acting on the pulley. Okay, like that T2 is equivalent to T1 plus T1. And here T1 in the right one, T1 equals W. Now here, in this situation, we have a mover that is trying to lift a piano slowly up to a second story, and he's using a rope that is looped over two pulleys, one of them, of course, to change the direction, and the other one, it is to reduce the forces that he's gonna use. Now, moving with constant velocity, sigma F equals 0, then this 2Ft, the forces of tension, they should be equal to mg. And from that, you will find that the Ft is mg divided by 2, which is 2,000 newtons divided by 2, which is 1,000 newton. Something that I want you to know, depending on how many number of pulleys, I will be able to calculate what is the force needed by calculating the number of I will say the number of strings that they are going up, and you will be able to reduce the force to 1/2, 1/3. It depends on the setup. Also, when I have connected objects here, remember, like if I apply a force here, like in this situation here, the two objects, they should accelerate with the same acceleration. Then here, like sometimes we will say maybe let's say I will say A1 and A2, but we know here actually is going to be also the same direction, but sometimes no. Then here A1 equals A2 and it should be 1A. Okay, because if you're gonna say A1 and A2 and you start solving your problems, you might find, oh, wow, I have too many unknowns. But of course, this is gonna be the case. The tension in between them is gonna be the same. Okay, and we know that the force and the masses, we will be able to find the acceleration of the system and also the tension in the string. Now, whenever we are going to have connected objects, I will say we need to create a free body diagrams. And free body diagrams, here they're gonna be two. This is mass 2 and this is mass 1. One of the general mistakes that we usually have is that we will consider that this force is going to act on M2. No, this is not correct. Now, for mass 1 only, we're going to have that force, the horizontal to the right, and there is the tension to the left. The same tension will be affecting box 2 to the right. Okay, then two separate, I will say, free body diagrams. We will apply two separate, I will say, Newton's second law. And then we will solve the equations together. You might have also friction, which is going to add more forces to the system. I will show you, like, there is another we'll say, version of that problem where I have one block is on a table and the other one, it is connected through the string, and mass 2 is accelerating downward, and of course, therefore, M1 is going to accelerate to the right. And this is the physical picture. You will draw free body diagram for the first one. You are going to create also free body diagram for the second one. You will create your equations and then you will solve them to calculate the acceleration and then the forces, any forces that we were asking for. Here we have the system called Atwood's machine. It is just simply that pulley here, and we have like two objects that they are different in mass. Okay, like you can look at this here. I can use, this is the system as if it is an elevator. Then I have an object and I have something called the counterweight, which is going to be on the other side. And like the weight of the elevator is more than the weight of the counterweight, and this is why we are going to have acceleration. We have acceleration of the elevator downwards, whereas we are going to have the acceleration of the counterweight upward. And here, just again, a reminder that the magnitudes are going to be the same, and this is the reason why I will call it A. But of course, as vectors, you're going to find them different because the direction is different. Now, and I will say, we assume that the cable's mass are negligible masses, and that the mass of the pulley as well as any friction is neglected. Now, I will say, what if the mass of the counterweight is 1,000 kilogram and the mass of the elevator with like 4 passengers, it is 1,150 kilograms. Then we want to calculate what's the acceleration of the elevator and the tension in the cable. You need to draw separate free body diagrams for the two objects, the two masses here. This is the first for mass, for the mass of the elevator. And this is, yes, for the mass of the elevator. Then let me use EE. Okay, and this is here EE. Okay, now I have T upwards minus ME G downwards, and I have the acceleration downward. This is the reason why I'm gonna put minus ME times A. And for mass 2, this is the situation. It's the same tension minus M2G, but this mass is gonna accelerate upward. And this is the reason why, okay, we call it counterweight. Then let's have it counterweight, counterweight, counterweight. Okay, now I have two equations. This is number 1 and this is number 2. Okay, where, oh yeah, here I don't have to have that. No, the acceleration is A. That's correct. Okay, I can solve these two equations. You can solve them using elimination, substitution, whatever method that you like. I did use here substitution. And then I was able to say that A is going to be mass 1 minus mass 2 divided by mass 1 plus mass 2 times G. And this is the calculation. Then this is for Atwood's machine. What about when I have the two objects are really connected and they are really connected through this incline, like one of them is resting on an inclined plane and the other one it is it is connected through the pulley, and then we have the mass. Okay, try this here. Try using this. And I will say we are going to get this one, okay, as the exit ticket for chapter 6, because I need to test you on how you are going to solve problems like this one. Okay, now I will say we were doing dynamics, but again, as I said, we're gonna go back a little bit to kinematics and talk about circular motion. And here we are going just to talk about objects that they are really moving with a constant speed. Okay, now we call this type of motion uniform circular motion. The reason it is with constant speed. Now, because the direction of my object is changing, keep on changing, I will say we need acceleration, and that acceleration, we call it centripetal acceleration. It should be pointing to the center, and this is the reason why we call it centripetal, or like sometimes we call it center seeking. Here, you can see in that picture here that I have my object initially here, then this is V1 and this is V2. I can draw, because remember the acceleration, it is V2 minus V1 as vectors divided by the time. Then the time is a scalar, is not going to affect, and you can subtract two vectors by finding the vector that is going to go from V1 to V2. This is the direction, and you can see it is towards the center. We call that centripetal acceleration or radial acceleration. And I will say the magnitude is going to be using a formula that is really very easy, very straightforward. I will say centripetal or radial, and it has to do with that constant speed divided by the radius of the motion. Then it's going to be V squared over R. Now, always if I want to keep an object in circular motion, I need a force that is required to keep it in that circle. The magnitude of that force, we call it again centripetal force, is going to be MACP, and that is going to be mv squared over r. Now, the nature of this force can be like that we might have so many different forces, like for the earth, for example, going around the sun. This is of course gravitational force. I can keep an object or like a stone moving in a circle by tension. I can use friction. I can use like so many things to keep it in motion, in circular motion. By the tension in the string, the normal force, friction, among others. The force toward the center must be supplied by other objects. Now, of course, here, something that I want you to know. If you are going to have, let's say in this picture, the string is going to be broken, you will see that the mass is going to fly tangent to the circle. Then if this is my circle and the object, and suddenly I have the string cutting off, the object is going to fly, and because now it's under no force initially, but finally is going to of course curve because of the it will curve based on gravity. I can okay, the centrifugal force, it is a fictitious force, it's not there. And I want to show you here also YouTube related to that concept, which is the one that I have already, I believe, I hope it did. Oh, it's gone. Okay, then it's gonna be physics, and it's gonna be the last one. We started the motion and the ball is going in circles, and then suddenly we will cut the string. We will cut the string. At any moment, it's gonna go according to the tangent at that point. The same idea. All right. Okay, now we want to solve one problem related to circular motion with this mass in a string. We have a 0.150 kilogram ball on the end of a 1.10 meter long cord. That is, we are neglecting its mass, is swung in a vertical circle. The first part, what is the minimum speed the ball must have at the top of its arcs so that the ball continues moving in a circle? And the second part, calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed of this part. Now, I will draw the free body diagram at the top. Sigma F, of course, should equal mv squared over r. I have the forces, both of them negatives, and the acceleration is in the negative y direction. This is the reason why I added negative mg, negative t, negative mv squared over r. But of course, I can cancel all these values, these negatives, and finally I will have my equation like this. At the top, T should be the minimum, otherwise the object will not be able to make it. And V squared will equal RG, and then V equals square root of RG, and I have calculated that speed to be 3.28. Of course, this is like here, it's not uniform circular motion. It is changing speed based on, going from one point to another. Now, the question is asking you if at the bottom the velocity is double, what is going to be the tension? Then I can now draw free body diagram for the object when it is down, when it is at the bottom, and we're going to have T upward, mg down, and the acceleration is going to be upward. Then I can calculate sigma F equals mv squared over r, and I will be able to calculate the force as 7.34. Now, when a car goes around the curve, there must be a net force towards the center of the circle. Here I will say if the road is flat, the force is supplied by friction. And maybe there is always a question, okay, the car is moving, why we're going to consider, let's say, the static friction? And the reason is that when we will consider the rolling motion of the tires is going to be when that tire is momentarily is going to be at rest when it have the contact with the ground, with the road. If the frictional force is insufficient, the car will tend to move more nearly in a straight line as the skid marks show. Then it's going to skid. As long as the tires do not slip, the friction is static. If the tires start to slip, the friction is going to be kinetic, which is bad in two ways. The kinetic frictional force is smaller than the static, and the static frictional force can point toward the center of the circle, but the kinetic frictional force opposes the direction of the motion, making it very difficult to regain control of the car and continue around the curve. And you have this in practice if you are going to speed up while you are going in that type of motion. Here we have a car that is rounding a curve on a flat road of radius 50 at a speed of 14 meters per second. Will the car follow the curve or it will skid? Now, we're going to assume first that the pavement is dry and the coefficient of static friction is mu s 0.6 and the pavement is icy and mu s is 0.25. Then I will say, and I will draw the free body diagram, which is drawn here, and I will say sigma F equal mv squared over r. The only force that is going to keep this is here, the radial direction is mu s mg, and this equals mv squared over r. Then my v squared is going to be mu s gr. Then the maximum velocity that can be here, it is 17.1. Then I will say it will follow the curve because I have a good driver who is sticking with the speed limit here, less than 17.1. Now, if we have that width, then the coefficient of static friction is 0.2, then the speed should be 5.72, and of course, apparently the car will skid and is going to be difficult to control. Now, if we are banking the road, means we are getting that curve and making it like the theta, the angle is going to be a certain theta. Banking the road means having an angle for that. We are going to make it, for most of the cars, not to skid. I will say for all the ramps that we have, there is one speed at which the entire centripetal force is supplied by the horizontal component of the normal force, and no friction is required. Okay, but if you are adding friction, if you adding more like secured driving. For example, for this car here, what is the angle for an expressway off-ramp curve of radius 50 at a design speed of 50 kilometers per hour? Now, the first problem here is, I will say, we need to convert, of course, that speed. You cannot have it in that unit. I did draw here the free body diagram and analyze the normal force into the radial direction is going to be Fn sine theta, and then I did apply sigma Fr equals mv squared over r, and this is Fn sine theta equals mv squared over r. I need the normal force, and this is the reason why I will also say sigma Fy equals 0. Then I got for the force of normal to be Fn equals mg over cosine, and I did solve the two problems together, and I found that v squared should equals rg times tan theta. From that you can calculate what is really the angle, and it was 21 degrees. Now, if we have an object that is not moving with uniform, then this is, I will say here, non-uniform. Non-uniform non-uniform motion means here I might have a tangential acceleration and also a radial acceleration. Then what we are going to get is the resultant, which is A total, and that A total can be calculated It can be calculated as a square root of AT, the tangential squared, plus the A radial squared. And of course, also you can measure that, like you can find that angle here, and that angle is going to be tan inverse of AR over AT. Okay, this is the summary of chapter 6. Friction is due to microscopic roughness. Kinetic friction, static friction, the maximum value is given here. Tension is the force transmitted through a string. The force exerted by an ideal spring is Fx. Remember, this is for the direction. An object is in translational equilibrium when the net force acting on it is 0. Connected objects, they should have the same acceleration, and the force required to move an object of mass m in a circle is force centripetal, mc centripetal equals mv